In the last class, we discussed the basics of deadlock and the resource allocation graph. Today, we move to the part 2 of deadlocks where we will be discussing the prevention methods, the deadlock avoidance method and the Banger's algorithm, and deadlock recovery methods and a possible detection. The three methods for handling deadlocks are deadlock prevention, deadlock avoidance, and when a deadlock is detected, the possible recovery from a deadlock. What is deadlock prevention? As the general meaning of prevention word suggests, it is escaping from deadlock before it occurs. Then avoidance is avoiding the possible situation of happening of a deadlock, and once both these situations fail, a deadlock occurs, and that is the deadlock detection and the methods for recovery from deadlock once it is detected. In the last class, we had seen that if four conditions hold good, a deadlock occurs. So, in the prevention methods, we have to take care of preventing all these conditions to occur simultaneously. First is mutual exclusion. What is mutual exclusion? That is, only one process can use a resource at a time, and the resources are not shared by the number of processes at a time. So what we are going to do as a preventive mechanism is to convert all the non-shareable resources to shareable resource. That is, we know it's not possible in all the cases, but in some cases non-shareable can be made to shareable forms. But in some cases, non-shareable resources like printers has to be kept as non-shareable itself. Then the second condition is hold and wait, and we are going to remove the hold and wait condition. How? A process requests the resource only when the process has no resource with it, and we can avoid the hold and wait situation. Then now we are going to prevent a non-preemption condition. Each process has to request and to be allocated all its resources before it begins execution. And if a process that is holding some resource requests another resource that cannot be immediately allocated to it, then all resources currently being held are released. And these preempted resources can be added to the list of resources for which the process is waiting. And in this way, we can avoid the hold and wait situation. Now we are going for the last condition of preventing a circular wait. What we are going to do here is to impose a total ordering of all the resource types and require that each process requests resources in an increasing order of enumeration. That is, a process requests an instance of resource type Rj. It has released a resource Ri such that Ri is greater than Rj. Then, in such situations, circular wait conditions cannot hold good. These are all the preventive measures which can be taken for deadlock. But we know that ideal situation cannot happen always, and we cannot prevent deadlocks. In such cases also, we can go for another measure of deadlock avoidance. Deadlock avoidance is escaping from a situation of deadlock, that is avoiding the situation of a deadlock. When a new process enters the system, it must declare the maximum number of each resource type that it may need. That is, it needs an additional a priori information for deadlock avoidance. And when we are designing some deadlock avoidance algorithms, it must dynamically examine the resource allocation state to ensure that there can never be a circular wait condition. When a user requests a set of resources, the system must determine whether the allocation will leave the system in a safe state. We will see what's a safe state. A system is in a safe state if there exists a sequence of processes P1 to Pn such that enough and sufficient resources can be allocated for the requesting processes. That is, currently available resources plus the resources held by all the processes can be sufficient. Then the system will be in a safe state. So what's an unsafe state? In the safe state, there is no possibility of deadlock. In the unsafe state, sufficient resources for allocation. And in the unsafe state, there may be possibility of deadlock. And deadlock avoidance is ensuring that the system will never enter an unsafe state. So in the avoidance part, what we are going to do is, we will ensure that always the system is in a safe state. A possibility of deadlock exists only when it moves to the unsafe state. So we are going to ensure that the system will be always in a safe state. One of the popular avoidance algorithm is the banker's algorithm. The banker's algorithm gets its name from the bank's procedure. Like, bank never allocates more than the available cash, that is the resource there. So a bank never allocates more than the available cash there. So here we are going to see, here we are going to do, we are not going to allocate more than the available resources. So this algorithm is a good algorithm when we have multiple instances of a resource type, and as we suggested, we will be having an a priori information, and maximum will be the process, and when a process enters the system, it must declare the maximum number of its resources and all the informations will be available. When a process gets all its resources, it must return them in a finite amount of time, ensuring that the resources are available for allocation. So in the banker's algorithm data structure, we have 4 terms: available, max, allocation and need. Available is a vector of length m, and we can see that available of j is equal to k. There are k instances of resource type rj available. Then max is an n by m matrix. What is this n and m stand for? N is the number of processes and m is the number of resources. So all these things will be clear once we see the algorithm. Then allocation is also an n by m matrix, and if allocation of ij is equal to k, then pi is currently allocated k instances of rj. Then need is also an n by m matrix. Then how we calculate need? Need of ij is equal to maximum of ij minus allocation of ij. So all these things will be clear once we move in deep to the algorithm.